hopefully some of you were able to come up with the right answer to this problem. And if you were able to do so, not only would you have found the number of different ways your teacher can fill these seats, what you would have found in math terms would have been the number of permutations for this problem. Permutations is a math vocab word that simply means the number of ways a set of data or numbers or a problem situation can be arranged in a particular order. Okay? What makes permutations so special, for our sake and for your sake for the next couple days, is that order matters. See that right here in the problem? Sitting at the end of the table is obviously very different than sitting in the middle of the table. So order is important. And when order is important, what you're finding is the number of permutations. When you think of permutations, think of permanent, because that order is permanent. It can't just be flipped around. Now, my guess is that in order to solve this problem, many of you simply made a list of the number of ways. So, let's do that together. We had Pam, Ryan, Sophie. They sat like that. Or if we had Pam and Sophie, then Ryan, we could have sat like that. Now, if Ryan was on the end, we could have Ryan, Sophie, and Pam. And then Ryan, Pam, Sophie. And then if Sophie was on the end, it would be Sophie, Pam, Ryan, or Sophie, Ryan, Pam. Okay. For this problem, the number of ways your teacher could organize the students back there, or the number of permutations, is simply 6. Okay? This is the first technique or possible way that you could solve a problem with permutations, is you make a list of the possible options. My guess is that's how most of you solve that problem. Perfectly fine. However, we're going to learn a couple other ways to solve these types of problems. So, moving on to a new situation. Let's say I had the word quiet, okay? And I want to know how many different ways can I arrange the letters in the word quiet. Let's say I'm making a jumble, and I want to know all the different ways that I can arrange these 5 letters, 2, 3, 4, 5, in any fashion, okay? Now, if I were to make a list of this, it would take quite a bit of time. I'd have to go through all the different examples with Q, U, I, T, E, that quite, or Q, U, T, I, E, and so on, and so on, and so on. So, in order to solve it in a quicker fashion, let's think about this problem. Quiet. It is a 5-letter word, which means there are 5 blanks we are filling in each time. If I was going to fill in the first blank, how many different letters could go here? 1, 2, 3, 4, 5. Any of these 5 could go here. So I have 5 letters that could go here. Alright, now the second blank, how many letters could go there? Well, it can't be 5 because I can't reuse any of the letters. So one of them has gone away. So now I only have 4 options. Same thing for the next one. I can't use even any of the first 2. So I only have 3 left, and 2 left, and 1 left. This is what we call in math the counting principle. You are simply counting the number of options for each of your spaces or each of your openings in a permutations problem. So if I have 5 here, 4 there, 3, 2, and 1, I just multiply those opportunities. Just the same way as when we used a list or a tree diagram early on, what I'm doing is I'm extending this for a larger problem. So if I have 5 times 4, it's 20. Times 3 is 60. Times 2 is equal to 120. Times 1 is obviously 120. So there are 120 different ways, or 120 different permutations for the word quiet. The jumble, people could put quiet in the jumble for 120 straight days and use a different organization of it each time. What we did right here, when we had 5 times 4 times 3 times 1, this counting principle is written in math like this. We call this a factorial. It is a number followed by an exclamation point. And what that means is you multiply that number by all other positive integers until you reach 1. So 5 factorial is 5 times 4 times 3 times 2 times 1, which we just figured out was 120. 4 factorial would be 4 times 3 times 2 times 1. 4 times 3 is 12, times 2 is 24. So whenever you have a problem that involves these permutations, you can make a list if it's a smaller one, or you could use what we'll call the counting principle. Which means you will simply find the factorial of your options. Hopefully this all makes sense. We're going to do another example together right now. Alright. Let's forget this quiet guy. And think about a baseball team. On a normal baseball team, there are 9 positions. Okay, so 9 players start each game. So if I was a manager of a baseball team, and I was calculating or making my lineup, I could have anyone bat in the positions from 1 through 9. You know, maybe the shortstop's going to lead off, followed by the center fielder, and then the first baseman bats 3rd. Maybe the pitcher will bat 9th, maybe the pitcher will bat 8th. Any of these different options are a potential lineup. As a manager, I want to know how many permutations or how many possible lineups I could have. I have 9 players that I know are going to start. How many different ways can I organize them in the lineup? This is a very similar problem to our problem on quiet. I simply can use the counting principle. Alright, 9 people could go here, 8 could go here, 7, 6, 5, 4, 3, 2, 1 person would be left. Or I could simply calculate 9 factorial. Some of you might have that on your calculator. If you do not, 9 factorial obviously is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now let's use a little bit of a shortcut here. When we did the problem on quiet, we realized that 5 factorial was 120. I'm going to cut off that work for myself right there. 5 factorial is 120. So let's see here. 120 is what this is. So I can figure out 9 times 8 times 7 times 6. I can just multiply those together and get my answer. So 9 times 8 is 72. 72 times 7 is 504. And 504 times 6 is 3,024. So if I have 3,024 times 120, first one would all be 0, 0, 8, 4, 0, 6, 0, 0, 4, 2, 0, 3, add them all up, 0, 8, 8, 2, 6, 3, or 368,880. If I wanted to, come over here to my calculator and make sure, once that loads, there it is, and this is right, 9 times 8 times 7 times 6 times 62880, which would be the same thing as 9 factorial. So, whenever you have a problem where that order does matter, we call it a permutation. And when you have a permutation, you can either make a list if it's a smaller problem, or you might choose to use the counting principle and therefore multiply the factorial of your number of options.